In this video, we're going to introduce the idea of building mathematical models of real-world situations using exponential functions, and then analysing them using what we know about exponentials and logarithms. Exponential growth and decay models can be used for many real-life situations. For example, the growth of a colony of bacteria or cells, animal cells, financial modelling of how money grows over time. Or in terms of decay, we could be looking at atmospheric pressure, drug dispersal through a body, and radioactive decay. An equation that can be used to model a population, for example, that grows exponentially is this one here, where we have n of t is equal to n0 e to the kt. Here, n of t is the population that is present after some time t. N with a subscript 0 on it is referred to as the initial population, because it's the population n when t is equal to 0. You can see this by substituting 0 into the function. An exponential to the power 0 is going to give us a 1 multiplied by n naught, thereby the initial population. K is a constant related to the rate at which the population grows. In the remainder of this video, we'll have a look at how we can use something like this to model a particular situation. So let's take a look at that example. A lab tech is monitoring bacteria, so a person in some sort of scientific laboratory. Initially, they've noted that there were 500 bacteria in the population, but then after 4 hours, there were 3,500 bacteria. Assuming that the population of bacteria grows exponentially, so assuming we can use an exponential growth model, the question is how many bacteria are present after 11 hours? How long would it take for the bacteria population to double? So there's two questions in that, and a fair bit of information which will help us to build our model. Now we already know that this video is about models of this kind. N of t equal to n naught e to the kt. So we're trying to build something like that. Take a moment now to reread the question yourself and think about how you might use the information to inform building that model. You might want to take a moment to write down the important information from the question and start to associate it with the parts of the model equation on the previous page. Here's a couple of things that I've picked up straight away. In the second sentence, the word initially is used. Initially refers to a point in time, the first point, or if we like, t equal to 0. Initially, we're told there were 500 bacteria. A number of bacteria is what we're looking at here, so it's probably good to associate the bacteria population as our n of t variable or function. So initially, if there are 500 bacteria, we can say that n at 0 is equal to 500. We're then told that after 4 hours, there were 3,500 bacteria. If t is our time in hours, we could write n of 4 is equal to 3,500. At this point, it might be good to start putting things into, or trying to force them into, the function for our model that we take from the previous page. The exponential growth model says that the population n at some point t in time is going to be equal to n0, the initial population, multiplied by e to the kt, where t is time and k is some constant that tells us about the rate of growth. The first thing we can pick out here is the initial population. n0, this constant sitting in our model, is actually equal to n at 0, so we can simply replace that one. On the other hand, the remaining quantity that we need to figure out, k, is not as easy to get at. So let's just write down our n naught first of all to give us our first starting point at the model, and then try to see how we can get at that k. Okay, all we've got that we can use is this other population and time point, time of 4 hours and population of 3,500 bacteria. If our model is going to work, it's going to need to have that set of values as one of its set of values. So in other words, when time is equal to 4, we need n of t to be equal to 3,500. In other words, 3,500 equal to n naught, or 500, e to the k times t, but where t is equal to 4 hours. So in other words, I've substituted in n equals 3500 and t equal to 4. As you can see, the only thing left over that we don't know in this equation is k. So now it's just a matter of solving for k by rearranging this equation. So we can start off by dividing both sides by 500 to get 3500 on 500 equal to e to the 4k. 3500 on 500 is just going to be 7. So 7 equals e to the 4k. Now having that k inside the index of our exponential function means we're going to have to use the inverse function for e, which is of course the natural log function. So we take the natural log of both sides, and that allows us to simply write that the natural log of e to the 4k is 4k. Finally, we can write down, by dividing both sides by 4, that k is equal to the natural log of 7 divided by 4. You can write that as a decimal if you like, but it'll go on forever, so I'm just going to keep it in this form. Now that's the only thing that we didn't know in our model, so we can now write down the full form of our population of bacteria model. N of t is equal to n0, or 500, e to the k, which we now know is the natural log of 7 on 4, times t. So that's our model for bacterial population growth. Jumping back to the question, it then says how many bacteria are present after 11 hours. So in other words, what is n of 11? So all we have to do here is use our model where t is equal to 11 and substitute that value in. 500 e to the log 7 over 4 times 11. Jumping out to your calculator, you should be able to find that that's approximately 105,436.17. Now we should finish this up and say that that's a whole number because we're talking about the number of bacteria. So we could say something like number of bacteria, and I'm going to round down, is 105,436. And that answers the first part of our question. How many bacteria are present after 11 hours? Something you might want to make sure is that it's well and truly more than the number of bacteria after 4 hours, remembering that our bacteria are growing exponentially. And it is, it's a lot bigger than 3,500. The second question asks, how long did it take for the bacteria population to double? Here the key is looking at how the question asks us how long, in other words, an amount of time. What is the amount of time, or what is the t-value, at which the bacteria population is double? In other words, what is the time when the bacteria population is not 500, but 1,000? So another way to express that might be, what is t when n of t is 1,000? Well, again, we're going to draw on the model that we've developed for bacteria here. The population equal to 1,000 is equal to the initial population multiplied by e to the k, but we remember that k is log 7 over 4, multiplied by the t-value. And we're in a very similar place to what we were when we solved for k. The only unknown that we've got in our equation here is t, and so we need to solve for t by rearranging and again using the inverse property on the exponential. So we have 1,000 divided by 500 is equal to 2, leaving us with e to the log 7 on 4 times t. Next we take the log of both sides, the natural log. Log of 2 is equal to the log of e to the log 7 on 4t. The logs and the e's will go away here because they're inverse functions, and we're left with log 7 on 4 multiplied by t. Finally, rearranging for t, we get 4 log 2 over log 7. Again, if you jump to your calculator, you should be able to find that that's approximately 1.42, and the units here are hours, and we can take that as our approximate time at which the population has doubled. So there we go, a first introductory effort at modelling with exponential functions. Here we've seen or introduced the exponential growth and the decay models. The example we looked at was an exponential growth model, but similar things can be done with exponential decay as well.